All right, everyone. Welcome back for the last session of the day. I guess RAM session still remains, but I more or less the last session of the main talks for the day. And in the session, the first talk will be given by Afonso on Check, a compact password authenticated key exchange protocol from lattice-based CAM.
Okay, thank you. So this is a joint work with Manuel Barbosa, Stanislav Yaretsky, and Marian Skobot. And I'm here to present you our new PAKE protocol called SHIK. Okay, so PAKE is a two-party protocol where two parties shared a low entropy secret. This low entropy secret can be a password or a PIN. And they execute this protocol, and they end up, if they execute it successfully, with a high entropy session key. And if they execute the protocol correctly with the same password, they should both end up with the same session key. And if they execute the protocol with different passwords, or if the protocol had some interference, they should end up with different session keys. So the security model usually demands that an adversary that is able to intercept message at will, replace some of these messages, should and interact with honest parties, should only be able to test one password per interaction with the honest party. So all this started more than 30 years ago with the work of Belavin and Merritt in 1992. And many protocols have since been proposed and multiple variants. And a little bit more recently, one of them, CPACE, was selected by the IATF as a symmetric PAKE protocol. And more recently, as we'll see, many works have been proposed and trying to upgrade PAKE protocols to post-quantum security. So throughout these years, we've seen also some real-world adoption of PAKE protocols. Most notably, we have PAKE protocols in electronic passports nowadays, in every electronic passport. We have PAKE protocols in Wi-Fi WPA3, and we even have industry adopting PAKE protocols as well. There are many more examples, so here I'm only focusing on the symmetric PAKEs, but if we go for a symmetric PAKE, there are many more examples of real-world adoption. And we've seen also real-world attacks on these protocols, notably Dragon Blood, that took advantage of timing attacks to be able to break through via side channels Wi-Fi WPA3. And as I said at the beginning, now there has been many recent works that try to leverage the new standardization efforts on post-quantum encapsulation mechanisms to try to produce PAKEs that are secure against quantum adversaries in some sense. And we had a lot of works, especially in the past 2 years, that compile CAM directly to PAKE. And our work here is one of these. Okay, so the interesting thing is all these works that appeared in the past few years, they all follow more or less one of two patterns. And these patterns, these design patterns have been proposed quite a long time ago. So one is the encrypted key exchange, which is actually the first PAKE protocol that was proposed. And its variant, one-way encrypted key exchange. So let me briefly just recall how this works in the CAM setting. So we have Alice and Bob. Alice generates a public key secret key pair. Alice then password encrypts her public key into something that we call APK and transmits APK over to Bob. Bob then password decrypts APK, retrieves Alice's public key, and then uses the CAM encapsulation mechanism to derive a key and a ciphertext, and then further re-encrypts the ciphertext or encrypts second layer over the ciphertext with the password they share, obtains key star, and finally derives the key. And then this ciphertext that is password encrypted of the ciphertext that encapsulates the key K is sent over to Alice. Alice can then password decrypt the ciphertext, decapsulates the ciphertext, and then derive the same key. The second design pattern is exactly the same, but instead of encrypting twice the ciphertext, so instead of re-encrypting the ciphertext, Bob simply derives a key and a tag directly, and this tag authenticates the ciphertext. Okay, so in all the works that we have seen in the past 2 years, they all follow either one design pattern or the other design pattern. So all the PAKE, all the CAM compilers that we have seen from last year and this year. So in our particular case, we decided to follow this one. So we have a ciphertext and a tag. So when I say password encrypt something, or password encrypt a public key or a ciphertext, the way that I described it before, it was with an ideal cipher. So usually in practice, when we want to instantiate an ideal cipher, we simply take an off-the-shelf block cipher. But in our case, what if we have to instantiate an ideal cipher over a group? Well, we have to be really careful to make sure that the domain of the ideal cipher coincides with the domain of its instantiation. Otherwise, it's quite trivial to come up with an offline dictionary attack. How would that work? Well, any adversary intercepting the first flow, so the authenticated public key, can then try to decrypt that APK with a candidate password. And if that candidate public key does not belong to the public key space, then the adversary can automatically discard that particular password. So when we look at CAM public keys, lattice-based CAM, we usually have public keys that look something like this. So we have a matrix that is then multiplied by some secret and added some error, and then T is the group element that will become the public key together with the matrix A. So one thing that we observe is that in most CAMs, a common optimization technique used is that in order to reduce the size of the public keys, instead of transmitting the whole matrix A, this matrix A is deterministically derived from a small seed. And therefore, the public key becomes a small seed with, for instance, 256 bits plus a group element T. So this group element is encoded with many coefficients in that are modulo Q, where for depending on the CAM, the Q might be prime or might not be prime. So for instance, this is the modulo used for MLCAM, Kyber, and we see that we need 12 bits to encode this one coefficient in ZQ. But the actual space is slightly smaller. So it's really non-trivial how to, especially when you have many of these coefficients, how to actually build an ideal cipher for such public keys. So in 2020, McCoy, Kozulek, and Hoy proposed a different approach that instead of using an ideal cipher to encrypt the public key, we could use a two-Feistel network to do so. So how would that work? You actually put your group element on this side and on the right wire, and you put some random coins on the left wire. And then these two hash functions that our model has random oracles only need to, in this case, map a bit string into a group element, and then this one simply maps back to a bit string. And essentially what this makes is that instead of having a one-to-one relation between the public key and the ciphertext, which now has two elements, we have a slightly enlarged ciphertext. So unfortunately, the solution with the two-Feistel network permits some sort of malleability, which seems insufficient for PAKE, or at least the abstraction that was proposed. The programmable ones public function seems insufficient to construct EEC and OEEC type PAKEs. And so Duchamp, Gu, and Yaretsky proposed to replace this XOR operation with an ideal cipher. So you might be wondering why we're replacing again with an ideal cipher. Well, because this particular ideal cipher is quite easy to instantiate. It's not an ideal cipher over groups. It's just an ideal cipher that takes some bit string and outputs another bit string. So it's quite easy to instantiate. Why is it called half ideal? Because this S component passes through an ideal function, so that part is completely random. And so looking at CAM public keys, so lattice-based CAM public keys, and looking at this half-ideal cipher construction, we were wondering, okay, could we split the public key into as such that instead of feeding only one wire, we actually feed both wires of the two-Feistel network. And in particular, when we look at Kyber or MLChem, now the standard public keys, we would like to split them such that this R corresponds to the small c that expands to a matrix A. So it already has this form that is needed and one group element. So the advantage of doing so is that now we have one public key and one ciphertext that are of the same size. So there's no expansion anymore on the ciphertext. And effectively what this does is we're essentially de-randomizing the half-ideal cipher because there's no external random coins used for this encryption. So in general, for this either EEC or OEEC construction, it is required that the public keys are uniformly distributed or look uniformly distributed. And so when now in this, and for the EEC construction, we know that this R part must also look uniformly distributed. So we combine the two notions of uniformity that are required for this into one single experiment, where we demand that the CAM public key, with respect to the split function that we use, produces these two elements that look uniformly distributed as compared to if we were to sample them independently. And one interesting thing about this approach is that we can now consider a split function that does not have to be deterministic. So we can even consider a split function that allows it to be randomized. And so in particular, if we have the split function that simply puts the identity on the right wire and some truly random coins on the left wire, well, essentially we're recovering the half-ideal cipher construction that was proposed. And the notion of uniformity is essentially, so this one is obviously uniform, so is essentially the standard notion of uniformity of public keys that we have for Kyber, which is also known as fuzziness. And another interesting thing is that although this optimization of starting with a small seed and expanding to the matrix A is used by multiple CAM schemes, not only MLChem. So for instance, ProtoChem also uses the same optimization, but unfortunately the seed that is defined in the specifications demands that it has a fixed size of 128 bits. But because in our proof we will require the ideal cipher to avoid collisions even across different keys. It means that this input and this output must be 256 bits, or at least 2 times the security parameter. So what this split functionality does is it allows us to use also other CAMs like FrodoCam that are not obviously compatible with this scheme by simply appending the number of random bits that we need to make it fit to the right size. So the downsides of this approach is that the half-ideal cipher requires that honest parties are unable to control this wire. And here, this wire comes directly from the public key. So we lose the abstraction of the half-ideal cipher. So to make our proof go through, we had to do a direct proof, meaning that instead of using an idealized object like the half-ideal cipher, we directly keep track of all the inputs and outputs of the idealized objects, like the two random oracles and the ideal cipher. So there's still the question about how to instantiate this hash function. So the whole idea is not having to instantiate an ideal cipher over a group, but we still have an hash function onto a group. And we can see that FrodoCam, for instance, has groups elements that can be encoded as bits because they're power of 2 modulus. And so we can simply take an extendable output function and just cut at the right place to be able to obtain a group element. But when we look at Kyber MLCam, then it's not so easy because now we have the elements that are modulus these coefficients. And as we've seen, this coefficient is not a power of 2. So how we instantiate this is with the same rejection sample procedure that is used by MLCam to sample the secret key public key pair at the beginning. And we use the same rejection sample procedure to map elements here to elements here. And so how does our protocol look at the end? Well, it looks very similar to the one-way EEC that we have seen at the beginning. So we have Alice that generates a secret key public key pair, then splits that public key into R and M so that it can feed both wires, then applies the password encrypts the public key by feeding both wires to this modified two-Feistel network, obtains SNT, and this SNT then becomes APK, which is sent to Bob. Bob then reverts the process, so by reversing the two-Feistel network, and then unsplitting the public key, and carries on with encapsulating and deriving a session key and attack. And the same happens after with Alice. So our protocol, we prove that our protocol UC realizes in the random oracle and ideal cipher model at PAKE, provided that CAM has these 3 properties, which are quite standard for CAM nowadays. So the first one is one-wayness of ciphertext. So this is strictly weaker than in CCA. We need anonymity of ciphertext, meaning that the ciphertext should not reveal the public key that it was used to produce the ciphertext. And for this, we need an actively secure CAM, meaning that it has to be at least plain text checkable. So this is also slightly weaker than the normal decryption oracle that you give in standard definitions. And then we require that the public keys look uniformly distributed. So we implemented this protocol to have a sense of how it performs compared to the underlying CAM. And now we have a protocol, a PAKE protocol that is almost as efficient as the underlying in CCA CAM. These examples are for Kyber. And we see that there's only a small overhead due to having to encrypt and password decrypt and derive a attack. And in terms of bandwidth, the only overhead that we have is the tag that needs to be transmitted from Bob to Alice. Otherwise, it's exactly, you just send one public on one sense and ciphertext plus the small tag on the other way. So one important question that we had, and I have been receiving a few comments on this, is that, okay, rejection sampling normally is not constant time, and this might be problematic. This is exactly the same problem that we had with Dragon Blood. So the way that we implemented, actually, we used exactly the key derivation function that was used in Kyber, but the problem is not only for our particular protocol. So any any Kyber to PAKE protocol, since the Kyber itself or since the underlying CAM uses rejection sampling, yes, we have to be careful with timing attacks. And so one way to mitigate this is the standard for Kyber CAM allows to fix the number of iterations to 280, which will then guarantee that it only fails with a really small probability, so we can fix the number of runs. There are more things to look into this, but that seems something that can be overcome. And once we overcome this problem of creating a constant time key generation algorithm, then we can use that same constant time key generation algorithm to instantiate our hash onto group function. So another remark that we have is that our ideal function, ideal cipher requires 256-bit blocks. And AES, as we know, has only been standardized for 128. So for this, we use Rindale 256 to overcome it. Another alternative would be to use domain extenders if we really must use AES. So funny thing is that I received a presentation from this last week where they seem inclined to actually standardize Rindale 256, so that might not be a problem in the near future. And finally, I think it's worth mentioning that our proof is in the random arc and ideal cipher model, so we don't allow quantum access to the idealized functions. But since the underlying key encapsulation mechanism is post-quantum secure, so at least we can guarantee that the harvest now, the crypt later attack can be mitigated with this protocol. And that's it. Thank you very much.
So we have some time for a quick question. So I can get started until someone wants to grab a mic.
Sure.
So the question that I have is that did you explore more trade-offs in terms of the overhead that you're paying? So you said that current overhead is only the tag, and then the performance overhead is about approximately a factor of 1.8 or 2.
Yes.
That's what I could see.
Yes.
So is there a trade-off that maybe you can either have a little bit of more tag length and maybe reduce the performance? I mean, I don't know what changes that would require to your protocol, but maybe did you explore that?
So the protocol, the bandwidth is very close to minimal because the only extra that we have if we want to start with a generic CAM is the tag. So, but that we could potentially get rid of the tag. It probably would require some sort of non-malleability of the underlying ciphertext to get rid of that. So we will have to see more about the encapsulation mechanism in order to be able to not have that tag. So that would be the trade-off. For computational trade-off, I think as you mentioned, 1.5, we're very close to what can be done.
Great, thank you. Any more questions? So there's one question over there.
Hello, it was a really nice presentation. Thank you for
Thank
it.
you.
Yeah, I have one question that you mentioned that rejection sampling is a problem for your scheme, the scheme you have designed. Have you ever considered the schemes the lattice-based schemes which doesn't use such rejection samplings?
Yeah.
Let's say for
Pro-
Saber.
Yes, or Frodochem, for
Yeah,
instance.
products.
So Frodochem doesn't require rejection sampling because the module is a power of 2.
Yes.
So you can simply cut on the right place and you know you have a group element that exactly has your needs. So if you use, if you instantiate this with Frodochem, yes, then you don't have any problems with timing attacks because the key generation algorithm there is also constant time. If you want to take advantage of something like Kyber that currently does not, I'm not aware of any implementation that is constant time for the key generation algorithm, then you have to be aware that potentially there's timing attacks to take care of there.
Thank
But
you.
if the underlying chem does not require rejection sampling and has a key generation algorithm that is constant time, because it's not only the instantiation of the hash function. So depending on where you can measure your time, if you can measure how long it takes for Alice to initiate the process and that reveals some information about the public key, then that also is problematic regardless of how you instantiate the hash function. So you really need all the key generation, encryption, and decryption algorithms to be constant time.
Okay, you need all those algorithms.
You need,
constant time.
yes. And usually the only one that is not always constant time is a key generation algorithm because it's usually not necessary for most applications that this is the case. But for this particular application, it would be wise to have a public key generation algorithm that is constant time.
Thank you.
Thank you.
Great. Let's thank the speaker again.
Okay.
Great. So it's my pleasure to introduce Stanislaw. He's going to tell us about augmented threshold PAKE, and it's a joint work with Yankee, Pavel, Philip, and Jiaoyu.
Hello, thank you for the introduction. Okay. So we are back at the question of password authentication key exchange. And just like Afonso said, we start with Beloved merit, and two parties submit passwords. And if the passwords are the same, they get the same key. Otherwise, they get two independent random numbers. And in this talk, we'll talk about the asymmetric version of a PAKE problem. So it was called augmented password authenticated key exchange, or APAKE, where one party, the server, has a hash of the password. And the functionality now checks whether Alice's password is the pre-image of the one-way hash function of the Charlie's hash, right? And why? Because if you set things this way, it's a corruption of the server only leaks the password through brute force dictionary attack, right? So you have to query this the hash function on password candidates until you get a candidate that hashes this value. And or that might never happen if the password is with chosen with high enough entropy. Then the sort of the golden standard is that in addition, this hash function is salted. So it is really a randomized hash function whose randomness is also stored on the server. And the difference from the previous picture is that the values of this function cannot be pre-computed. You need the randomness before you can compute these hash values. So the dictionary attack cannot be pre-computed, and it's independent for every user account. And this should compete against the password over TLS kind of authentication, right? Where the server has public key, user essentially encrypts the password over this public key and it gets shipped here, and then there's a local check and the server decides whether the user is authenticated or not. But this leads to phishing attacks. The user essentially encrypts the password under, whatever certificate keys that are derived from a certificate that she believes in. Maybe she makes a mistake during this assessment. Also, passwords are effectively processed in the clear on the server, so some implementation bugs. And there were attacks. Of course, there's many famous phishing attacks, and they happen all the time. And then there are attacks on the server side where, even though this check was being performed through some memory dumps, or attackers were able to get a database of clear text passwords. And a protocol of this nature was created by myself and Hu Krawczyk and Zhao Xiu, and we have gotten this. It was called PAKE, and IETF chose it for like a PAKE standard in some sense to adopt. So here in this talk, we will try to make this stronger. And how? Well, so if the server is compromised, then you can make offline dictionary attacks. So this could be made stronger by thresholdizing this part, right? So do not store this value in a single place, but secret share it, and then emulate the server with multi-party computation. And this type of approach is called threshold password authenticated key exchange. So, okay, so there were prior work on threshold PAKE, but they essentially secret shared the symmetric PAKE. So rather than secret sharing this value, they really just secret share the password itself. So now we have incomparable properties, because the single server PAKE, after corruption of this guy, you get one-way function of the password, right? Whereas with distribution, if you corrupt T+1 servers, you get the password in the clear. So we would like to secret share the augmented PAKE, in effect, secret share the state of the server, right? So rather than having this in the clear, we'll have a secret sharing, and this group is secret sharing this this information. So if some bunch of these characters get corrupted, well, if fewer, if at most T, then there should be no information. And if T+1 or more, then they reconstruct this information, at which point they don't get password in the clear, but only then they can do offline password tests. Some choices of like what you want the system to provide. For example, so this key, who gets among these people? There is Alice gets some key, and who amongst them gets the K prime? Well, we said, let's have a designated server called a target of authentication, whereas all the other servers are only providing like an auxiliary type of service. They exist only to secret share this information so that it doesn't sit in one place. So the system is not, it's not subject to, I mean, that you have this is secure computation, and the information is secret shared. So this was the so-called gateway server in some prior TPAKE work. For initialization, we assume that all the state is simply created by the end user. So she has a password, she's going to share it, she's going to create these values, secret share them, and so we simplified the initialization this way. We assume that during the PAKE, threshold PAKE execution, these parties will have some session identifier, and if this is inconsistent, the session will not go through. And also, we support explicit authentication. So who among these people learns whether or not her key is the same as that one? In other words, that her preimage really did satisfy this equation, against this secret shared information. And we say only this target server learns that. Okay, but at the same time, these guys could also play the role of a target server. So if you wanted explicit authentication to information to be there, they could play the target server roles as well. So the schemes that we propose have some further benefits, and this is they are very low interaction. So user basically sends one message to these guys, and she receives one response, after which she just directly talks through the TS. Moreover, the second step is a black box. So between the user and the TS, we can run any APAKE, or even authenticated key exchange, or even a password over TLS, although this would get weaker security. We allow a proactive security, so this secret sharing can be refreshed proactively. The schemes allow multiple target servers, and with something called partial oblivious threshold PRF, these guys can have a constant state and service arbitrary many user accounts with it. So now we move to how. Yes, so I'll show you two strong APAKE protocols that are basically like, this one is opaque and this one is like opaque prime, very, very similar, but slightly different. So, okay, how does opaque work? The users pick so first it's based on something called oblivious PRF. In other words, a PRF that is accompanied by an efficient two-party evaluation protocol where the server has the key and the user has the argument, and the user is going to compute the PRF value. So now at initialization state, user picks the key of the PRF, computes the PRF on her password, and then uses this password for authenticated encryption to encrypt two things: private key of her key exchange. So this is an authenticated key exchange scheme. So like if you think like, for example, triple Diffie-Hellman, then this is just a Diffie-Hellman key, and this is another Diffie-Hellman key, right? So this is G to the A, and this is G to the B. Okay, so she encrypts her own private key and the server's public key under this output of the PRF. We call it an envelope, and what sits on the server side is the PRF key, the envelope, the private key of the server, and the public key of the client. And the opaque protocol goes like this. First, Alice, with the password, she engages in this oblivious PRF evaluation, where server contributes the PRF key. So she learns, she retrieves this value through this two-party secure computation. Now, the server also sends to her the envelope, so she recovers from the envelope her private key and the server's public key, and now she uses arbitrary secure authenticated key exchange. So, for example, 3DH or like Signal, yeah, to get a key. Now, this protocol is very similar, except that there is no envelope. Instead, you start with an augmented PAKE, and which you initialize on this PRF output. So you treat this PRF output not as a key, as in this case, but as a password. Yes, so this is basically a hash of this value treated as a password. And that's what's stored. The OPRF step is the same, but what this block is changed into the augmented PAKE. Okay, but it's not a privately sorted augmented PAKE. It's just private. It's just a basic augmented PAKE. Okay, so they have some differences. This guy starts with a stronger primitive because it's slightly harder to construct, right? But for many for many key exchanges, it's basically the same cost. And but it has a nice benefit that the user doesn't learn whether she's successful before the server does. So this is a more standard behavior that this scheme supports. Okay, here's how we do a threshold version of it in this paper. So first, we need the threshold OPRF evaluation protocol. The key will be secret shared, and this will be a distributed protocol. She, on her password, will be able to retrieve this value, but the servers will secret share the key K. And so, where is it now? Okay, so we basically propose something called like threshold of PAKE. It's a threshold of PRF, and the rest is the same. So the key is secret shared. The servers store a secret sharing of this key, and which servers they are? Well, these are the auxiliary servers. This first group of n servers. Okay, so she retrieves the same value as before, but now in interaction with T+1 of the auxiliary servers, and the rest is the same. The envelope and this stuff is just what's stored at the target server. So the target server is the one who will be executing this part, and therefore he will be the one who will create a shared key with Alice, right? So it's very, very similar. You just replace this block, the OPRF, with a threshold OPRF, and you have a natural division between auxiliary servers and a target server. And you can do the same over here. This is a secret shared, this is a secret shared, this is the threshold protocol. Again, this is done by auxiliary, and this part is done by the target server. Basically, everything falls if you replace the OPRF with the threshold OPRF. There's different variants of this that we analyze in this paper. For example, this could be a strong APEC as well, and you get slightly better properties from that. This could be even the password over TLS. So, if this stuff is not adopted, you could still use these threshold schemes to improve the current security. And we have a slightly different sort of version here. This is called augmented password protected secret sharing. And actually, one of my co-authors, Pavel, is going to talk about this block in a related talk tomorrow about password protected threshold signatures. Okay, so this partial of PRF allows the servers to have the single sharing of the key K and service multiple user accounts with it. Maybe I sort of should skip this. So this, because of the very black box nature of this, so this is this OPRF we model as a UC kind of beast. These are standard protocols, so it just security follows from the black box nature of these compositions. And okay, so let me just move to the POPRF block in the remaining time, and we revisit this paper, which I also participate and Xiaowu, and this is Rishab and Aguilar-Skias. And there was not quite right this model that we proposed in 2017. In particular, we noticed that, so first of all, we didn't have adaptive security. And as you can see from the nature of these games, the whole games are sort of concerned about attacks on these servers, which really should be modeled adaptively. So that was something we needed to get fixed. I mean, upgrade. But in the process of upgrade, we also noticed that there's problems in the way this UC functionality was defined. And this is a little obscure. So the essential thing was that this functionality didn't, when in ideal world where the user said, I want to perform a T threshold of PRF, she didn't have to specify with whom. So if she had two concurrent sessions where all these guys were involved in, the simulator didn't know which half works for one session and which half works for the other. And this basically makes the ideal and the real diverge. It's maybe an obscure issue, but it's sort of like, if some of these servers agree for the session to go through, you don't want like a mix and match that the adversary somehow can choose. There is, it's not like we have an explicit attack, but the modeling was not quite right. And you can see that it was making choices which basically make the model ambiguous. Here is how we fixed this in this paper. So the basic single server OPRF that we support here looks like this. It's the hash of the argument exponentiated to the key. It is easy to secret share, right? Because every server can just exponentiate this value to the, then this is the blind exponentiation protocol. She blinds to the exponent, and then she's going to remove this blinding here. And she's going to use the standard interpolation to evaluate this. And because the sum of these values, right, reconstructs the key, she's going to reconstruct hash of x to the k here. But there is a problem. This is information theoretic hiding over what is the x. So the simulator, when she is asking many servers, and notice that she can use a different blinding factor for every message she sends. So therefore, this would be completely independent random group elements, and the simulator has no idea which of these values correspond to the same x. Here is a sort of funny fix. So we secret share a sort of a shadow value called z that is secret sharing a 0. It's a randomized secret sharing of a 0. And we use this blinding factor, which essentially enforces that unless she uses the same A for a group of T+1 servers, their responses will be diverging. They will be masked by independent values here. So they will not reconstruct. But if she uses the same A for T+1, then this is the same blinding factors that they all use. This will be interpolating to a 0 because the ZIs are 0 shares. So this blinding factor will disappear. So this is like an implicit way to force her to send the same A to T+1 people. This could be handled by an extra, broadcast and Byzantine agreement, right? But this is just to, obviously doing it non-interactively speeds up. And by the way, the very similar trick was used by Das and Ren recently for a very different purpose. Adaptively secure BLS, threshold BLS, and it's sort of funny confluence of the technique, but actually for a different technical purpose. So I will end with the slide because I'm out of time. Thank you.
Any questions from the audience? All right, let's thank the speaker again. Thank you so much. All right. So the next talk is on key exchange in the post-Snowden era, universally composable subversion resilient PAKE. And the talk is by Lorenzo.
Thanks for the introduction. And yeah, today I'm going to briefly present some of the main ideas behind this first PAKE protocol in this somewhat crazy framework, right, of subversion, resilience, universally composability. And this is a work jointly done with Shurati Chakraborty, Bernardo Magri, and Daniele Venturi. So this is the outline for today. I'm just going to give a very brief introduction to subversion so that we're all on the same page, and then we'll have a quick stroll through the main results and challenges of this work. So, as we all know, secure MPC is great, right? Because it allows parties to jointly compute functionalities, all while preserving, of course, the privacy of their inputs, yeah? And in particular, we can very well define protocols that retain this kind of security assurances, even if a subset of parties may be corrupted. And I mean, in general, models, are treated as having parties that can be honest, semi-honest, or malicious. And in particular, for the negative side, this is great, right? Because actually, malicious corruptions are very general, and they allow to tackle several potential real-world attacks, even potentially unknown one to date, while, of course, providing meaningful security guarantees to the respective honest party. However, on the other side of the coin, honest parties are not necessarily as clear, right? Because it turns out that indeed, the mere idea of a honest party is that it should run the protocol is exactly as per the prescription of the protocol, which for certain cases can be unrealistic in practice, right? Because a protocol will be implemented in software, we'll have a software stack, a hardware stack, and there are many entities that are all interacting in this building of this complex ecosystem, let's say. So it could very well be the case that something goes wrong at some point. And so one possible way to, let's say, provide a more fine-grained analysis approach would consist in separating the actual entity who is running the protocol, so let's say the user, the operator of the machine, from the actual machine itself. And that's also kind of what subversion really boils down to, in a sense. So while we can have that Bob is malicious as before, Alice may very well be honest, right? But actually, her machine may be somewhat uncooperative. And this somewhat kind of depends on the class of subversions that are being considered. For this talk, we will consider the so-called specious subversions or undetectable subversions, which are basically subversion attacks that are undetectable to the honest user that is actually using the machine. So in particular, Alice can test this machine in a black box fashion, and if she determines that its behavior is indistinguishable from a honest machine, then she just proceeds with running actually the protocol, yeah? And again, this is realistic, yeah, because if Alice is well-educated and does her homework, that's something she would be interested in doing, because of course, if this implementation just deviates arbitrarily from the protocol, she could just throw it away, give up on the secure MPC, and just go back to pen and paper, yeah? So what can concretely happen even with such a restricted class of subversion is that, for instance, the machine of Alice could attempt to exfiltrate information by some kind of subliminal channel, right? So there could be some message that is identically, that is distributed as what a honest machine would output. And once this is received by the adversary, either by eavesdropping on the channel or actually by having the adversary participating in the protocol run, this could very well cause a leak of some of Alice's secrets. And again, a prototypical attack would be, for instance, rejection sampling, right? So Alice shoots a ciphertext of some nature, and now this implementation will instead do some rejection sampling up until the ciphertext has a specific structure that may be decoded successfully from that person. One way to go around this issue consists in equipping each party with these so-called cryptographic reverse firewalls, which were first formalized by Mironov and Stephen Davidowitz in 2014, and later extended and formalized to the UC framework rather recently in 2022 by Chakraborty and others. And the idea here is that each party is equipped with this kind of objects that kind of do what you would expect them to do, right? So they should sanitize the traffic, that's the point. So they should run some re-randomization of the messages that are being produced by the machine, so that, of course, the protocol will still run to conclusion, of course, while preserving correctness. And one important thing that I want to stress is that these are not trusted third parties. So in particular, this subversion resilient UC framework allows to provide meaningful degrees of security, even for instance, if the core is honest and its firewall is semi-honest. And that's basically also to kill any potential trivial instantiation in which the core is just sending their input to the firewall, and then the firewall will actually run the protocol on behalf of the core. So with that out of the way, we can move to our actual contributions. And from a very high-level standpoint, what's happening is that we are showing a sanitized protocol that kind of starts from this PAKE from OT that appeared in PKC 2012 due to Canetti and others, which fundamentally is structured in two steps. First, they construct PAKE from OT assuming authenticated communication, which is also called randomized equality, and then they remove these authenticated channels in a generic fashion. This protocol kind of relies on this fundamental building block, let's say, which roughly goes as follows. There is a party who picks two random strings, and the responder for a 1-bit password will just provide their bit of the password as input to the OT. And the idea is that these random values will actually be used to determine the key. Of course, these two parties will be able to agree on the same value only if they actually know the same password bit. Yeah. Of course, this is just for 1 bit. What's actually happening in the protocol is that this happens for every bit of the password, and both parties should do that because otherwise one party has full control of the key. But again, that's what we want to focus on. And even in this very simple building block, there is already some issue while moving to the subversion setting. And you can very well expect that the issue is in OT. The reason behind that is due to the actual definition of OT, right? Because OT, again, from a semantic standpoint, is a functionality that allows a party to receive one of the inputs of the other party unchanged. And now we saw that we needed some random values, for instance, in the protocol before. So, of course, if these two inputs are sampled in a bad way or lead to some leakage of information, Bob, with malicious, will just retrieve them, and this causes a leak. So we're kind of screwed, right? I mean, we cannot really use OT. This is just an ideal functionality. So again, it's not like firewalls can really intervene to try to save the day. And thankfully, that's also where the subversion resilient UC framework comes in. And the idea consists in instead of instantiating just the plain OT functionality, we want to instantiate a different notion of ideal functionality that is called these sanitizable ideal functionalities, which very roughly give firewalls a mechanism, an interface to, let's say, operate on the inner state of the ideal functionality. So in particular, for the case of OT, what these firewalls are actually doing is that they're basically intervening in the ideal functionality by blinding each of the sender's inputs, so that the receiver will instead receive a blinding of the chosen input rather than just a plain input. What we show in the paper is actually something slightly more general, which additionally allows Bob's firewall to blind the sender's inputs. And this kind of gives a better protocol structure for the final PAKE protocol. And again, this comes more or less for free because, again, as we are about to see, these firewalls can be instantiated by both parties, and they have essentially the same structure. Okay, so how do we instantiate this thing then? And the starting point was this protocol for OT due to PVW, which relies on dual mode crypto systems, which very roughly are public key crypto systems that additionally have this notion of encryption branches. As you can see, the receiver here is producing a keeper for such a crypto system by also specifying a choice bit. And this choice bit will be basically the encryption branch of choice of the receiver that will be used for the remainder of the protocol. The sender, instead, just by having access to the public and to the CRS, can produce ciphertexts on each of these encryption branches, which will be true in this case, but this can be generalized. And now the receiver will be able to decrypt exclusively the ciphertext that was associated with the original bit choice, while of course revealing no information about the other input. So this gives OT in a very natural manner in traditional UC, let's say. And that's indeed what we want to start from in order to actually build our sanitizability functionality. So what are the ingredients? First of all, we need to add firewalls. We will just represent one here for simplicity, but actually both firewalls are running the same code. And of course, the first thing we have to do is that we need to sanitize the public key. So in order to do that, we kind of augmented these dual mode crypto systems by introducing 3 additional algorithms. The first one is the small PK algorithm, which essentially for now just produces a new public key that is uniformly distributed over the key space. And in a sense, this is also adding what I'm referring to as a layer of sanitation here, because of course now the sender is producing ciphertext, but the receiver cannot really decrypt because these ciphertexts were generated with a different public key. The second algorithm that we need, of course, is, very natural. We need to do some homomorphic operation on ciphertexts, even while preserving these encryption branches, because we have to blind, of course, the sender's inputs as well as the ciphertexts, right? So that after this input sanitation phase, this firewall basically is producing 2 ciphertexts that are actually free from any kind of sidechain, let's say. And finally, of course, we have this layer of sanitation we need to get rid of that. And that's why we're also introducing a third algorithm that kind of just reverse the sanitation that was operated so that ciphertexts can now be decrypted with the correct secret key, so that now the receiver is happy. And it turns out that this is actually not too crazy to realize. This is just, we just followed the original instantiation from DDH due to PVW and kind of extended it with these new algorithms. So again, this is something that can be meaningfully instantiated. And we show that more explicitly on the paper. And once we have this building block, we kind of get PAKE by sanitizing the building block that we saw before, yeah? So we can realize basically a protocol that realizes the randomized equality ideal functionality, even in the presence of subversion, by assuming this building block. Of course, there are some subtleties that have to be accounted for because this sanitizability functionality is, is semantically different compared to the original key. And again, there are more details on the paper, but the high-level idea is that the blinding factors that are being introduced in some of the blocks of this oblivious transfer are being reduced elsewhere. And this is safe due to the fact that OT itself will not reveal anything about the other input. So you can also see that there is another block here, and that's this FSAT functionality, which is the subversion resilient UC equivalent to the F-alpha ideal functionality, which represent authenticated communication. And in these last few minutes, I just want very briefly to touch upon this topic as well, because of course now we have a protocol for randomized equality and we want PAKE, right? So in standard UC, what happens if we kill authenticated channels? Of course, if we cannot really have access to anything else, such as a PKI or stuff like that, the best we can hope for is something that was formalized with this notion of split ideal functionalities due to Barak and others in 2005. And the idea here is that the worst the adversary can do is partition parties before the protocol run. To be more clear, these 2 parties are trying to establish a channel they want to exchange messages on, and then either the adversary allows them to, of course, link, and then this behaves as just a plain authenticated channel, or it impersonates the peer of each part. The idea is that each party is really oblivious to that, right? So each party has the guarantee that it will be interacting with the same entity throughout the protocol run, but actually doesn't know whether this is the adversary or not. And this is reasonable, right? Because we don't really have access to any long-term secrets, long-term keys or anything. So yeah. And actually the way to realize this notion is quite natural as well, comes from, once again, from this work of Barak and others. And the idea is that each party just samples a key pair for a UFCMA signature scheme and sends the verification key into the void, yeah, right? This verification key will basically act as an identifier of the party. And now each party has to produce a signature that contains the set of identifiers that have been collected by that party. So that essentially, in order for this party to proceed with the actual protocol run, it has some guarantee that the other party has actually received its identifier, and actually it has produced a signature on that. So what we additionally show in this paper is how to port all this stuff in the SRUC framework. First of all, there is this concept, right, of isn't this concept? Yeah, but okay, thanks. Let's start. I mean, apparently it's not willing to cooperate yet. Okay, good. Not going beyond this slide for some reason. Yeah. Yeah.
We apologize for technical difficulties. No, they're saying that if you go to the program page of Asiacrypt and just click on your slides, and I think they're saying that you can access your full slides using that. Is that correct? So could you just do that rather than transferring using the USB stick? Just go to the program. Can you just go to the Asiacrypt program page, click on his slides on that page? Somebody in the audience is saying that the slides are uploaded, correct slides are over there. Can you check? There are more than 54 slides there. 68, great. Thank you. Yeah, that should be fine. Can you just move him to, I think slide 54? Yes. This seems to be a different talk or what? It's a different talk. You have to click the right track. It's track 2, right? Track 2, please. '68. Okay, great. Let's go for it. Slide 54, please. Can you just go to 54 directly rather than can you just go exit full screen and type 54 at the top? Yeah, just 54. 54. Good, great, excellent. We're back. All right. Oh. Unfortunately, we'll just have the next speaker should just get ready. You can ask him questions offline. So just maybe it'd be nice if you can just be ready. Oh, it's online. Okay, all right, great. Cool, thanks. Okay, so let's just get back.
Okay. Okay, so we're back. Yeah, as I was saying, yeah, there is this this protocol, right? So we're talking about this this sending verification keys that works that will kind of work as identifiers, and now parties basically have to sign on the set of identifier they're collecting, so that each party has some insurance that the peer they're communicating with is actually indeed producing what they would expect. Okay. Yeah, that's fine. Yeah, we can do that too. Yeah, okay. So, yeah, I can just say next. Yeah. Okay, yeah. Can you go back to a couple of slides? Okay, good. So, in the context of this aversion resilient UC framework, of course, now we need to clarify what actually these channels are among these new entities that we've introduced. And the idea is that there will be secure channels between a core and its firewall and the authenticated channels among firewalls. And I mean, the idea behind that is that we cannot really have anything less between core and its firewall. And that's because if we just assumed anything, let's say, less secure than that, the adversary could just eavesdrop onto that channel and immediately nullify the behavior of, I mean, rather the sanitation operated from the firewall itself, yeah? So in particular, again, if this is suspicious and it's leaking something, now the adversary can just report directly from that channel. So in order to move to this split setting, what we can have to do is kill the authenticated channels between firewalls. And the way we do that is by showing a sanitation of the protocol we saw before. So the idea is quite similar to what we saw for OT. So we need to, of course, blind the verification keys and then align the signatures so that one can verify the signature even under a different verification key that is still related to the original one. And in doing that, we also improved on an open problem that was there from the seminal work, given that this FSAT functionality was actually never properly instantiated or realized, rather only a sketch was given of it. So in a sense, we kind of shed a bit more light on what it actually, I mean, what's actually the backbone of communication in this framework. And so that at the end of the day, what we can do is that we can take our cool little protocol we had before and just remove authenticated channels in favor of these unauthenticated, I mean, rather in this split authenticated channels, so that essentially the adversary will first partition parties before the protocol run, and then it will kind of have access to two password guesses, right? Because in the case above, of course, there is no longer any way to man in the middle or try to do anything like that. In the case above, the adversary can indeed impersonate each party so that you can obtain your two password guesses by running two sessions of the protocol in parallel. So wrapping up, these were some of the main ideas behind the first PAKE protocol, and we introduced some new sanitation-friendly primitives. So we had some, I mean, funny ideas and stuff like that. Sanitizable oblivious transfer, this extension of dual mode crypto systems. On the paper, there's also a lot more for what concerns basically the specific instantiation of actual the complete protocol and some additional primitives, as well as proofs, of course, which are quite similar to the original protocols, of course, modulo this variation. I just want to conclude by saying that, as you can imagine, this framework is extremely recent and it's in its very early stages. So, and indeed, as you could have seen from this presentation, fundamental building blocks such as oblivious transfer are not even well defined yet. Were not well defined prior to this work. So there's lots of work that has to be done. I mean, so if you're willing to take a jump into that, that's, I mean, there's really, really lots of stuff to be done. So thanks a lot. And yeah.
Thanks, Lorenzo. Unfortunately, you'll have to ask him questions offline, and we'll have to just move to the next talk. Is it a recorded talk or is it going to be on Zoom?
Hello, can you hear me?
Yes, we can hear you. Probably.
Okay.
Zoom.
Can you see the slides? Can you see the slides?
The tech team here is working on it. Just give us a minute.
Okay.
I think we can see your slides. Can you move yours to the next slide just to make sure that we... Okay, great. Yes. Your slides work.
Yeah, okay.
Let's talk on efficient asymmetric PAKE compiler from Chem and authenticated encryption, and the talk is being given by you. Go ahead, you.
Thanks for the introduction. Hello, everyone. I'm Yu Lü from Shanghai Jiao Tong University. Today, I will share our work efficient asymmetric PAKE compiler from Chem and AE. This is a joint work with Shengli Liu and Shuai Han. First, I will introduce the asymmetric PAKE and its UC security. Then I will show our PAKE compiler and its security analysis in the random oracle model. Finally, I will show the efficiency of our PAKE scheme and give a conclusion. So password authenticated key change allows two parties to establish a secure session key with a shared low entropy password. PAKE allows parties to authenticate each other and exchange a pseudo-random session key. Note that the password only has lower entropy, so the adversary can always implement online invocations of the PAKE protocol with guessing passwords. The security of PAKE protocol requires this online password guessing attack is the only efficient attack. In other words, PAKE must resist offline dictionary attack. Recall that in PAKE, the server stores the plain passwords. If the server is compromised, then the adversary can impersonate the client immediately. While in asymmetric PAKE, the server has to store a password file. And now if the server is compromised, the adversary only gets the password file rather than the plain password. After the server is compromised, the adversary can try a password and compute the trying password file, and then check whether the guessing password is correct. And the security of APAC requires, after the server is compromised, the above offline dictionary attack is the only efficient attack beyond the online dictionary attack. In other words, the asymmetric PAKE requires that the adversary cannot impersonate a client unless it finds the correct password by the above brute force search. Now I will briefly introduce the UC security model of APAC. In the real world, the environment C first inputs password into each client and server. Then the client and server can run the APAC protocol. And here the adversary serves as a public network. It can insert, drop, or modify any message. And finally, each party computes a session key and return it to the environment. Well, in the ideal world, the client and server became dummy party. And we need to construct a simulator such that it can simulate indistinguishable transcript of APAC protocol in the real world. And it can also simulate indistinguishable output session key for each client or server instance. And we require that the simulator has no information of password, except two oracles. The test password oracle models the online password guessing attack. It will tell the simulator whether a guessing password is correct. And the simulator can only query this oracle once for a client or server instance. And the offline test password oracle models the offline brute force search attack after the server is compromised. Suppose the adversary issues at most Q random oracle query in the real world, then the simulator can query the offline test password oracle at most Q times. The UC framework is preferable to the AND model in the two aspects. First, the UC framework allows arbitrary password distributions, while AND model assumes passwords uniformly distributed over a dictionary. Second, the UC framework enables a smooth and secure composition with other UC secure protocols. As far as we know, there are no concrete construction for UC secure asymmetric PAKE scheme directly from post-quantum assumptions. There exists some compilers that can turn PAKE or AKE into asymmetric PAKE. However, the last three compiler has no lattice-based instantiations. The first signature-based compiler can give a lattice-based APAC scheme, but lattice-based signature are not as efficient as CAM. So our goal is to design an efficient APAC scheme instantiable from lattice. And in this paper, we give a new generic compiler for UC secure APAC in the random oracle model. We show that an APAC scheme can build up from a UC secure PAK, a one-way PCA secure CAM, and a one-time secure authenticated encryption. Our compiler can give an efficient APAC scheme from lattice. And our compiler can also provide mutual explicit authentication, even if the underlying PAK only has implicit authentication. Our compiler also has good round efficiency. If the last message of the underlying PAK is from server to client, then the APAC from our compiler only requires one additional round message from client to server. And finally, our compiler is tightness preserving. If the underlying PAK and CAM has tight security, then the APAC scheme also has tight security. Now I will show our APAC compiler and give a brief security analysis. During the registration phase, the server first computes RW and R as 2 hash values from the password. Then it takes R as the randomness of the key generation algorithm of CAM and obtains the public key PK and secret key SK. Finally, the server stores RW and PK as its password file. And when the client wants to exchange a session key with the server, it first derives the RW and the randomness R from its password. And then the client and the server can run a PAKE protocol using RW as a password. And finally, they can get a PAKE session key K0. After computing the PAKE session key K0, the server derives 2 additional keys, key 1 and key 2. It also encapsulates a key, key 3, using the public key PK in its password file. Then the server uses key 1 as the secret key of the authenticated encryption scheme to encrypt the ciphertext C. And finally, the server sends PSI to the client. When receiving the ciphertext PSI from the server, the client first uses K1 as the secret key to decrypt the key encapsulation C. If the ciphertext is invalid, then the client will reject the session and abort. Otherwise, the client can derive the CAM's secret key to decapsulate the ciphertext C and guess the K3. And finally, the client can compute a hash value of K0, K3, and transcript as an authenticated token. And the client will set K2 as its session key. And if the authentication token is invalid, then the server will reject the session and abort. Otherwise, the server sets Key2 as the apex session key. And now I will give a brief security analysis. Recall that our goal is to construct a simulator such that it can simulate indistinguishable transcript and session key without the knowledge of password. We first assume the server has not been compromised yet. And since the underlying PAKE has UC security, we can just consider the online password guessing attack on it. If the adversary guesses the correct password RW of the PAKE, then the simulator can extract the correct password RW with the help of random oracle. And now with the correct password, the simulator can simulate the transcript and the session key perfectly. And now consider the case that it makes a wrong password guess on PAKE. Due to the UC security of the underlying PAKE, the PAKE session key K0 is uniformly distributed. And therefore, the derived key K1 and K2 are also uniformly distributed. Then by the one-time CCA security of the authenticated encryption, the message PSI can be simulated by an encryption of a dummy message. And by the uniformity of K0 and the random oracle, the message sigma can be simulated by a uniform string. In this case, the apex session key K2 is also uniformly distributed. And therefore, the simulator can simulate the transcript PSI and sigma and the session key K2 without knowledge of password. And here we stress the necessity of the underlying authenticated encryption scheme. If we don't use the AE to encrypt the ciphertext C, there will be an offline attack. The adversary can try every password in the dictionary and then generates a key pair PKSK using the hash value of the password as the randomness. And then it checks whether the the ciphertext C is a valid encapsulation under the public key PK. And if yes, then the adversary finds the correct password. For example, if the underlying CAM is Kyber with the secret key, the adversary can easily check whether the ciphertext is encrypted by the public key PK, because Kyber has a re-encryption check introduced by the FO transformation. So the authenticated encryption scheme is necessary. And besides, the authenticated encryption provides explicit authentication. Now we consider the security after the server is compromised. The adversary cannot get information of password from previous session because the underlying PAK has forward security. Even if the adversary gets the underlying PAK password RW, the PAK session key still looks random to the adversary. So the PSI sigma and the session key of previous session do not reveal the information of password. And now A gets the password file, so it can always impersonate the server. And we need to show it cannot impersonate the client unless it queries each password for the correct password. And the high-level idea is, if the adversary does not query each password and it can send a valid sigma, then it must break the one-way PCA security of the underlying CAM. The adversary does not query each password means it does not know the CAM's secret key SK. In this case, if the adversary sends a valid sigma, it must query the key K3 in the random oracle. And this breaks the one-wayness of the CAM. And the plain text checking oracle is used to keep consistency in the reduction. And now the simulation can go through without the knowledge of password. And we show that the adversary cannot impersonate the client unless it queries the each password for the correct password. And this means the adversary cannot, and the simulator can simulate the transcript and the session key without knowledge of password. And this means the adversary cannot get the information of password in the transcript or the session key. So the only way of A is to try different password and query the each password using a brute force search. And this is exactly what APAC wants. And recall that our compiler uses two building blocks, a one-way PCA, secure CAM, and a one-time secure authenticated encryption. And the one-time secure AE has efficient information theoretical instantiations. So most of the security loss is from CAM. And if the underlying CAM has tight security under multi-user, multi-challenging setting, and the underlying PAK has tight security, we can obtain a tightly secure APAC protocol. And such tight CAM and PAK scheme exists under the matrix DDH assumption. At last, we compare our work with some related work and give some future directions. We compare our compiler with the signature-based compiler using the same EKE-based PAK from Lattice. As shown in the table, our compiler has better efficiency than the signature-based compiler from lattice-based assumption. And our APAC protocol is also comparable to the OPAC, but our APAC cannot resist pre-computation attacks. And finally, I will give a conclusion. In this paper, we design an efficient APAC compiler instantiable from Lattice. Our compiler has UC security, good round efficiency, and provides mutual explicit authentication. However, our APAC is not a strong one. It cannot resist a pre-computation attack. So one challenging question is, how to construct a strong asymmetric PAKE from lattice-based assumptions. And another question is whether it's possible to prove security of a PAKE in the quantum random oracle model. And for more information, please refer to the full version of our paper. And thank you.
Thank you very much. So you was able to sort of give us a lot of time for asking some questions. So do we have some questions from the audience? So I just have one quick question. Can you hear me?
Yeah, I can hear you.
So are there any technical challenges in trying to execute the proof in the QROM model? I mean, can you sort of use the standard recording approach for QROM queries and make the proof go through? Or is there kind of like a technical barrier in PAKE setting that prevents you from proving security in the case of for these PAKE things in QROM?
Yeah, I think a difficulty in QROM just in the asymmetric PAKE setting is, I think the model needs some adapt, because in the APEX setting it says the adversary query Q times random oracle, and it can equivalent to Q times brute force search on the password file. But in quantum random oracle model, we just need about squared Q since the Groover algorithm. So I think maybe we need a new security model to capture this.
All right. Thank you so much. If there are no other questions, then let's just thank all speakers from the session. Great. That's the end of the session. And I think now we have a business meeting after a short break.